Greetings, fellow learners. In this video, we are going to take a look at reinforcement learning. We'll start with some definitions, then go through some learning procedures, and even some code along the way. It's going to be fun, so let's get to it. Reinforcement learning is learning what to do, that is, how to map situations to actions, so as to maximize a numerical reward signal. This is a very high-level definition of reinforcement learning that's given in this book on the Introduction to Reinforcement Learning by Dr. Richard Sutton. You can see here that reinforcement learning is a method of learning, and a method of learning in machine learning is known as a paradigm of machine learning. And there are three core paradigms of machine learning out there, along with many other subcategories. The first category is supervised learning, where we have some data and we have some label associated with that data, and we give our dumb model hundreds of thousands of examples to learn how to associate that data to some label. And this is typically seen in classification problems and regression problems. And here are just a couple of tasks. In the unsupervised learning case, we have data itself, but we don't have any labels associated with that data. And these are typically used for understanding certain patterns within the data, as we would with clustering. Or it can be used in dimensionality reduction, among others. Now, reinforcement learning is that third paradigm of how machines learn, where, let me repeat, that reinforcement learning is learning what to do, that is how to map situations to actions, so as to maximize a numerical reward signal. Until fairly recently, reinforcement learning has been predominantly used in learning Atari games. So for example, this is the game Pong, where we have a paddle at the bottom, and we are trying to learn, as you know, the Pong paddle to actually play the game, so as to maximize the reward signal, that is to play the game very well. Now, initially it starts out bad, but as time goes on, you can see that this paddle is now able to effectively play the game much better. Another application of reinforcement learning that we see typically is a robot trying to learn how to walk in an environment. It'll do some trials and errors trying to interact with the environment. It'll continue to fail, but eventually it will get better. However, more recently, reinforcement learning has also had a very important role to play in the large language models today, like ChatGPT. So this is the model page for ChatGPT. And we see that they use a method of reinforcement learning, specifically called reinforcement learning through human feedback. And the goal of this is to ensure that the responses that ChatGPT produces are safe and useful. This here is the agent-environment interaction loop that is the core of many machine learning problems. The agent performs some action and interacts with the environment, and on doing so, the environment will emit a state and a reward, which the agent uses to influence its next action, and the loop goes on. Now let's talk about this from the perspective of the agent being a self-driving car. So in this case, if the agent is a self-driving car, it can perform certain actions. Now, these actions can be discrete actions like turn left, turn right, go straight, or they can be a set of continuous actions like, okay, turn your steering wheel by 38.6 degrees, by 38.7 degrees, 38.8 degrees. And it performs this in an environment. The environment here is traffic, and each instantaneous point in the environment is known as a state. So for example, a single snapshot of the environment, which is the state, can be represented by what are the cars in the next lane? What are the cars in the right lane? How far is a stoplight? Is there a car in front of you? Along with many other information that we can capture with traffic. Note that when it comes to traffic, however, we cannot truly understand how the entire traffic layout is, just from the position of a car's perspective. And this means that the environment is partially observable because we cannot construct a perfect and complete state of that traffic scenario from the car's vantage point. However, environments can also be fully observable, and this is in the case of an agent that knows how to play chess. In the game of chess, the agent has like a bird's eye view of where every single pawn is that is black and white, and can use all of that information in order to decide what action, that is what move, to make next. And there's really no other information beyond what is beyond this 8x8 board. So the agent at every stage has access to all information about the environment, and hence this is a fully observable environment. Next up here is we have a reward. A reward is an immediate gratification or punishment that is received by the agent on performing some action. So let's say that while the agent is driving and decides to turn left. Now, the reward that the agent will get will be a positive reward if the agent turns left onto, another road and it doesn't hit any pedestrian or it doesn't go on the sidewalks. Whereas it would be a negative reward if it does hit a pedestrian or it does cross a stop sign or it crosses a red light and performing other traffic violations. And this may influence how the agent behaves next. Now, let's talk about another few more complex elements here. Now, policy. A policy determines how an agent behaves in a certain situation. More formally, it is a function that maps a state to an action. Let's say in the self-driving car case, the self-driving car is there, and about 50 feet in front of it, there is a car that has completely stopped. That is a part of the state. Now, the car sees this, it takes it in, and its policy would return what action to be performed in this state. And that is, the action could be pressing the brakes so as to slow down and eventually stop. And hence, the policy influences how an agent should behave given a state. Reinforcement learning strategies can be either on policy or off policy. And I'm going to describe this using a simpler example, such as you trying to ride a bicycle for the first time. So you get on the bicycle for the first time and you want to try to learn how to ride it. Well, one way to do it is you get on the bicycle and you just roll with it. You kind of struggle a little bit. There are times when, let's say, you maybe turn a little bit towards the right and your bike feels like it's going to fall. But at that point, your mind is like, okay, I want to stay up. So I will lean towards the left, and then the bike now stands back up. And you continue to struggle, but eventually, as you keep practicing by trial and error, you will learn how to ride a bike. So in this situation, more formally, like the state would be, the bicycle is almost lopsiding. But during that state, your policy would be, given this state that my bike is lopsiding, I will choose the action of straightening my body towards the left. That is the action that you perform, and hence that is your policy. And you are using your previous actions to guide how you perform next. And that's how you will start, eventually learning how to ride the bike. Because you are using your own policy to repeat and train yourself, this is an on-policy method of reinforcement learning. Now let's go to the off-policy method. Instead of just taking the bike and just riding with it, you might look at somebody else around you, look at them, how they ride the bike, and you see how they're struggling, and you are learning basically vicariously through someone else riding. Now you can pick up the bike and start riding. But even though you make a little bit of mistakes, you are not adjusting yourself based on your past actions. You are adjusting yourself based on what you have learned from some other actions, from some other person's policy. And because you have learned offline how how to ride a bike using someone else's policy that is not your own, this method of learning is off-policy reinforcement learning. They have their own advantages and disadvantages. For learning on policy, let's say like in the self-driving car case, it might be a little too risky to directly just interact with the environment and try to learn from nothing and learn just by trial and error, because your car would start hitting obstacles, hitting pedestrians before it starts getting better, which might be a non-starter. However, with off policy, you need to make sure that you're actually taking the time to collect some form of training data that is useful to your reinforcement learning agent in your environment. Depending on how you weather these pros and cons, one or another of these on policy or off policy strategies would be right for your case. Next, let's talk about returns. So a return is the cumulative reward over time. And it's good to quantify the overarching goal of your agent. And high returns would indicate a sequence of actions that got the car to the destination without any accidents, any traffic violations, and in a short amount of time. So the goal of our agent would be to maximize this return. And then we have a value function that quantifies the expected value of return. Typically, it's the basis of maximization for certain models such as like Q-learning, which we try to optimize this value function itself. Reinforcement learning algorithms can also be bifurcated based on whether they are model-free reinforcement learning or model-based reinforcement learning. In model-based reinforcement learning, we use a model, and this model is supposed to simulate the environment around it. So for example, in our self-driving car case, a model-based reinforcement learning approach would create a model to simulate traffic. This can help our car make decisions and help better plan on how to attack real traffic when it deals with it. With model-free reinforcement learning, surprise, surprise, it has no model. That is, that there is no simulation of an environment that our agent interacts with. Instead, the agent will directly interact with the real environment and make some learnings from there. Now, which strategy to use also depends on your situation. With model-free reinforcement learning, we interact with environments, so we don't need to deal with the hassle of creating an environment setup, as we would in model-based reinforcement learning, which may or may not even be possible in some cases. However, with model-free reinforcement learning, we're just going to need to be careful of how we interact with the environment so we can appropriately learn safely. Policy optimization and Q-learning strategies are by far some of the most important model-free reinforcement learning strategies. In fact, if we look back at ChatGPT's model card, they do use proximal policy optimization in order to ensure that the responses that come from ChatGPT are non-toxic and are safe. If you want more information on how exactly ChatGPT works, explaining this entire model card in great detail, I have a video right over here. Consider the following problem. You are faced repeatedly with a choice among k different options or actions, and after each choice you receive a numerical reward chosen from a stationary probability distribution that depends on the action that you selected. Your objective is to maximize the expected total reward over some period of time, for example, over 1,000 action selections or time steps. This is the original formulation of the K-armed bandit problem or the multi-armed bandit problem. You could see here that it is a learning problem. So where do these K-armed bandits fit into the big picture of machine learning? Let's take a step back. Methods to solve machine learning problems are machine learning paradigms, and there are 3 core machine learning paradigms along with many others. But the first, probably more popular one, is supervised learning, where we have data and a label, and we feed this to a dumb model to help it learn how to map that data to that specific label. Classification and regression problems fall under this paradigm of solving problems, and here are a few tasks. Another machine learning paradigm is unsupervised learning, where we have data, but we don't have any label, and the goal here is to understand and learn patterns within the data itself. And this is typically used for clustering tasks or in dimensionality reduction, among many others. And then the third paradigm is reinforcement learning. Reinforcement learning is learning what to do, that is how to map situations to actions, so as to maximize a numerical reward signal. This is a generic definition of a reinforcement learning solution to a problem. Now, coming back to the definition of the K-armed bandit problem, we can see that the K-armed bandit problem is actually a specific instance of this broader reinforcement learning problem. At the end of the day, it is a learning problem that maps a situation, that is the situation of having K options in front of you, to an action where we choose some action here. And the choice of this action would optimize some reward over time. And that's exactly what we see here by optimizing the expected total reward over many time steps, like 1,000 time steps. To better understand multi-armed bandits, let's consider the situation where we are walking into a casino and there are 4 slot machines, and our goal is to walk out with the most money. But to simplify this entire case, let's say that for every slot machine we play, we either win or we lose. And so our goal, redefined now, is to walk out of the casino after playing 1,000 times with the most wins that we can possibly garner. Now, looking at this situation, the first slot machine over here, there's a 70% chance that if we play it, we win. There's a 30% chance to play the second one to win, 55 for the third one, and 40 for the fourth one. In order to get the most number of wins, if we knew all of this information, we would just go directly to that first slot machine and just keep playing it 1,000 times. We'll win approximately 700 times, but that'll probably be, on average, the maximum amount that we could possibly win. However, walking into a casino, we know nothing about this information. We don't know these numbers, these probability of successes. So how do we learn? So the idea here is first to do some exploration, that is, try to figure out which slot machine is good for you by randomly selecting them. And then the second step is exploitation, where now that we have a good idea of which slot machines work well, we can just start going to the ones that we have seen worked well historically. The multi-armed bandit problem requires us to balance both exploration and exploitation because they are both important. Why is exploration important? Well, let's say that we start playing slot machine 2 and we won. This might encourage us, oh, we won here, so why not just keep playing slot machine 2 for 2 times, 3 times, 4 times, let's say 10 times in a row. We won playing slot machine 2, which is possible. This might make us think, okay, we've seen like 10 of these. I think we are good to go all in on slot machine 2. But in reality, if we go all in with slot machine 2 1,000 times, in the long run, that is after playing 1,000 games, we would really only win about 300 games. So a fully exploitation system is not good, and this is why exploration is important. But the flip side is also true. Let's say that we're exploring all the time. That means that we are not really taking advantage of what we know, but just randomly choosing slot machines. So in this case, this would be like we played this one 250 times, this one 250 times, this third one 250 times, and the fourth one 250 times. Now, if you add all these numbers up, if you add all of your wins up, you might get a reasonable number of wins, maybe around like 400 to 500 wins, but it's definitely not the best that we could have possibly done. And so the balance between exploration and exploitation is absolutely critical when dealing with the multi-armed bandit solution. Let's now take a look at the code for multi-armed bandits. So the logic I just explained is actually being almost exactly regurgitated in this code. And note that this code is not mine. I put the link to the original author in the Colab notebook, but I'll also update and upload this notebook to GitHub myself because I've added just a few more pieces of information regarding like how large each of these elements are. So it might be a good reference too. In this case, we are considering 10 arms instead of the 4 arms, where each of these are probabilities of success. So going for the first slot machine will give you a 10% chance of actually winning. Second slot machine is 50% chance. Third is 60% chance, and so on. Now note that these are probabilities that we do not know going into this. This is only for the purpose of a simulation because we need some ground truth to actually understand if we're doing well or not. Number of steps is the number of times that we're going to play the slot machines over and over and over. I said 1,000 before, but in this case, we can take 500. Number of experiments is essentially the number of times we're going to execute these sets of 500 steps. So this is just for the sake of a simulation. EPS here is the balance between exploration and exploitation we want. We're saying 10% of the time we want to explore, 90% of the time we want to exploit our own knowledge. R is going to hold the total rewards for each time step, and A is going to hold the total number of times an action was performed in that time step. Now, for every single simulation that we perform, we're going to perform the experiment. This experiment involves choosing a slot machine, playing it, and realizing either a win or a loss. In the code, that's kind of exactly what's happening here. We perform an action, that is choosing a slot machine, which can either be exploration or exploitation. We then realize a reward, which could either be 0 or 1, depending on the probability of success that we described before of that slot machine. And then we perform these sets of actions and get rewards 500 times in order to get a list of 500 actions and rewards. This is now this would have been just one simulation, and we add the numbers for all simulations, where eventually with rewards, we're going to determine the average reward for every single time step. And if we plot the average reward for every single time step, we will get this graph. So this x-axis is the time step from 0 to 500, and then the average reward across all simulations is just this y-axis. Each reward would thus represent how well we did on average for a specific time step. For example, on average for, let's say, the 50th time step, we used to get an average reward for every slot machine that we played around like 0.64. But as time increased, you can see that our average reward did in fact increase. That means that we were making better decisions to actually take advantage of slot machines that truly gave us the best option win. It plateaus at 0.75, which makes sense because the best bandit arm, even if you chose that repeatedly, we would get 0.8. That is the highest possible reward and accuracy we could possibly get. And in a similar situation, we can also plot what were the slot machines that we actually chose at every time step. You can see in the beginning, we were very random in choosing our slot machines. But as we got more and more knowledge, even early on, you could see that we are definitely choosing this red line and then this gold line. So red line is arm 4 and the gold line is arm 9, both of which make sense because they truly had the higher probabilities of success. And though we didn't know this, we figured it out through rounds of exploration, and eventually we could start exploiting them to actually get those rewards. And that's why we choose these arms more and more over time, and that's also why we see that these rewards get better and better over time. In this video, we're going to talk about how we can solve problems with reinforcement learning. So machine learning is the ability of machines to learn to perform a certain task. And there are primarily 3 ways we can have machines learn to do different tasks, called machine learning paradigms. And these are supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, we have data, we have a label, and we have a dumb model that learns to map from the input data to the output label. And this is the foundation of classification tasks and regression tasks. Then in unsupervised learning, we have data, but we don't have the labels. And this is primarily used to understand patterns within data, primarily used in clustering and dimensionality reduction. And then we have reinforcement learning. Reinforcement learning is learning what to do, that is how to map situations to actions so as to maximize a numerical reward signal. Now, this definition is great, but it's kind of vague, and the idea now is how exactly do I go about thinking about building a robot that knows how to navigate the world, or building some game AI? We can do so with a theoretical framework called a Markov decision process. Let's start with the simple definition. A Markov decision process is a theoretical framework that you can use to solve many problems with reinforcement learning. And here is a visual of that MDP. In a Markov decision process, we have two main characters, that is an agent and an environment. So the agent will perform some action in an environment, and the environment in turn will emit a state and a reward. And this is consumed by the agent and influences the agent's next action, and so on. So this is a schematic of the Markov decision process. It is Markov because the next state that is emitted by the environment only depends on the previous state and action. In other words, it's memoryless, and past states beyond the current state don't really influence this future state. Decision in Markov decision process refers to the fact that we select an action based on the current state. And this leads to a state transition and the accumulation of rewards. And then we have a process in Markov decision process. Process emphasizes the interaction between the agent and the environment as a sequence of steps. So the agent's decision and the consequences of those decisions unfold as a process where each step is influenced by the current state and action. This setup gives more of a concrete starting point to think about solving problems with reinforcement learning. And so when thinking about this problem and solving it with this mindset of the MDP framework, we need to define the agent, environment, action space, the state space, and the rewards. So let's do that considering a few distinct cases. So let's say in this first case, we want to create a robot that can clean the room. And so let's go on defining the components of the Markov decision process. So we have an agent, that is the Roomba itself. Then we have an environment, and this is the room. And the actions that the Roomba can perform are, it could be turning 1 degree, turning 2 degrees, turning 3 degrees, turning 4 degrees, until maybe like turning 179 degrees. And then it can also be in the opposite direction of turning -1 degree, turning -2 degrees, and then up to turning -179 degrees. And another action could be just to move forward. Next, we want to define what is the state. So a state is a snapshot of the environment. And in this case, it'll be a snapshot of the room itself. So this could be the list of, for every single degree, is there an obstacle within 6 inches? Within 1 degree, 2 degrees, 3 degrees, is there an obstacle within 6 inches? It could also be how much charge the Roomba has, or how far is the Roomba from the charging port. And the reward, this could be the volume of dust that is collected in the container. And the idea here is that the more dust that is in the container, that means more the room has been cleaned, and it goes in tandem to achieve the goal that we set out for this Roomba. And now that we've defined all of these components, it is a matter of just now collecting data and coding things out from here. Now, it's important to note here that we don't really need to think in the realm of AI. The Markov decision process can go much beyond this. For example, consider a case 2 where a human is riding a bike and the goal here is to learn how to ride a bike. The agent is the human, the environment is the bike, which is on a road. The actions could be to pedal, to brake, lean left, lean right, turn left, or turn right, or continue straight. Now, the state is a snapshot of the human on the bike on the road. Is there an obstacle 12 feet forward, or immediately to the left and immediately to the right? It could also be the direction of our destination. And next, reward. So this could be 0 for every time step that the bike is straight up. We can get a negative 50 reward for if the bike slants a lot, or a negative 100 reward if we crash or fall down. And all of this will incentivize our agent to, well, be upwards so that it can maximize the reward. Now, another important thing to note here is that this is just one way to define a solution to how to ride a bike. It's not the be-all, end-all, and an extreme example would have framed it kind of like this, where the agent could be the brain, and the environment is the body, which is on the bike. The actions are send signal to the left hand, send signal to the right hand, send signal to the left leg, send signal to the right leg. And the state, which is the snapshot of the body, could be how elevated are the legs and the hands? Are there any tensions that exist in the muscles? How clear is our vision? And the reward would be what is the absolute difference between the current heart rate and the acceptable heart rate for riding a bike. So clearly it's very fluid on how we define what an agent and environment is, even for the same problem. Now, once we have defined these, it makes it much easier to understand what strategy we need to use to code this out and answer questions like, what architecture should the agent be? We have discrete actions, so what is the best for this? But like I mentioned before building all of this out, we need to phrase the problem with this framework, and the rest will fall into place. In this video, we're going to talk about the Bellman equation, but because this is a very specific topic, I want to show how this Bellman equation actually fits into the bigger picture of reinforcement learning. So let's start at the top. Reinforcement learning is learning what to do, that is how to map situations to actions, so as to maximize a numerical reward signal. This can be done in multiple ways, and so we can subcategorize reinforcement learning algorithms into two main parts. One are value-based methods, and the other is policy-based methods. Value-based methods will determine a value function that quantifies the reward, and using this value function, we determine an optimal policy. Policy-based methods will determine an optimal policy directly. And by optimal policy, it is the policy that maximizes the total reward. But wait, what is policy? So simply put, a policy is how does an agent behave in a given situation. Example of value-based methods includes Q-learning, deep Q networks, and SARSA, that is state action reward state action. Example of policy-based methods include reinforce, PPO, that is proximal policy optimization, or TRPO, that is trust region policy optimization. For this video though, we are interested in value-based methods as some of them make use of the Bellman equation. So value-based functions determine a value function, which in turn is used to determine a policy that will maximize total rewards. The value function is a function, so it has an input and some outputs. Depending on the inputs, there are two types of value functions. One of them is the state value function, represented by V, and then we have the state action value function, represented by Q. Wait, what are states and actions? A state is a snapshot of an environment that the agent is in, and an action is the decision taken by the agent in the environment. The state value function will take the state as input and output a real number. The state action value function will take the state and current action as an input and then output a real number. This real number is known as a Q value. The state value VFS will quantify how good is it to be in the state S. The state action value, or Q value, will quantify how good is it to be in the state S and take an action A. The equation of the state value looks like this, whereas the equation of the state action value looks like this. And as complex as they look, it's actually very intuitive. We'll now start explaining the intuition with a simple example and then come back to how we can write it as these mathematical formula. Let's say that we are in a fully observable environment where the agent is in its first grid, and the goal is to get to this last grid. The last grid has a 10 reward, and there's a poison space next to it that has a negative 10 reward. Other areas will have a reward of -1. From the current state, let's say that we're in the first cell and the current state is S1. We can then perform the action to go right and end up in a state S2, or we can perform the action to go down and end up in a state S4. Now remember, we want to perform the action that will give the maximum value, because remember, we want to maximize total reward. The value of being in this first cell of state S1 is equal to the reward that is obtained when we transition to the state S1 plus the maximum future value. And this is represented in math right here. The maximum here will depend on the action that we take. This seems really simple, but in actually more real world and complex situations, performing an action in one state doesn't always mean we will end up in the next specific state. And this is stochasticity. So this means that if we are in state S1, just because we move right doesn't mean that we're gonna go to S2 for sure. There might be like a 20% chance we go to S2, a 30% chance we go to S3, a 10% chance we get to S4, and so on. But we can represent stochastic environments with probabilities, and so we compute expected values for these value functions. And so if we perform a specific action, it'll be the sum of probability of transitioning to a given state times the value of that next state. And in general, we could, instead of just saying right or down, we could just give it a generic action A. This is similar to the textbook equation with two main differences. The first is that the textbook has a gamma term. This gamma term is known as a discount factor, and it will quantify how important are the current rewards obtained versus the future rewards that are obtained. And it will discount the future rewards because it's a number between 0 and 1. And the other difference is that we see that the reward R is added in between here. This is because in the textbook, they assume that the reward is also a function of the action taken, and so we need to put that into the equation altogether. But in our case, we're just assuming that it's a function of the state only and not the action, and so this can be written in a slightly different way. Now, we can determine this value function, but how do we determine the next action to take? We can determine the next action to take depending on the action A that gave us the highest expected value overall. So that is the highest sum of products and value function. Now let's do the same for the state action values, or Q values. For these Q values, we need to account for the state and the action taken in that state. So going back to our simple world, we are at state S1 and we apply an action of right. This means that we will end up in another state. For this simple world, like we mentioned before, it's pretty easy that we will end up in a state S2. And if we go down, we would have ended up in a state S4. The maximum reward in state S1 when going right is the reward in state S1 plus the maximum future reward in state S2. From the next state S2, we can perform any action, and hence we would take a maximum across some action A dash, which is taken in the next state. And that's how we end up with this equation. But as we mentioned before, for the more complex case, making the action A1, which is right, doesn't necessarily mean we will end up in S2. And going down doesn't mean that we're going to end up in S4, because this environment is stochastic. And we can represent stochastic environments with probabilities, and we compute expected values of these state action value functions. And the expected value is the sum of probability of transitioning to the state and the value of that state. And since this is a Q value, this would be the value of state and any future action that we take. But here we can see that the probability term doesn't depend on the future action A dash. So we can take it out. And once again, with the differences mentioned before, this becomes the original textbook equation. So to summarize this video, reinforcement learning algorithms can be subcategorized as value-based methods and policy-based methods. Value-based methods will determine a value function that quantifies the total reward. And using this value function, we can determine the optimal policy. The value function can be a state value function, that is V, or a state action value function, which is Q. The Bellman equation is a recursive strategy to calculate the value function. It is used by some value-based methods like Q-learning. Other value-based methods might use other techniques to determine these value functions. Hello everyone, and welcome to another episode of Code Emporium, where we're going to talk about Q-learning, arguably one of the most popular concepts in reinforcement learning. So let's get to it. Now, throughout the series on reinforcement learning, which you can check the playlist down in the description below, we have discussed that machines can learn in primarily three different ways, which are known as the machine learning paradigms. So the first one is supervised learning. That is, we have a dumb model, we have data, we have a label, we use that to train said dumb model in order to recognize patterns between the data and the label. And this is primarily used in classification and regression type problems. The second is unsupervised learning, where we have data, but we don't have a label, and the primary objective is to understand patterns within the data. So this is used in clustering and dimensionality reduction, among others. And then the third pillar is reinforcement learning. From the textbook, reinforcement learning is learning what to do, that is how to map situations to actions, so as to maximize a numerical reward signal. Now, we can break reinforcement learning algorithms down into two types, that is the value-based methods and the policy-based methods. Remember, at the end of the day, we're trying to maximize total reward. So value-based methods will determine a value function that quantifies this total reward, and using this value function, it'll determine the optimal policy. Policy-based methods will determine an optimal policy directly, and optimal policy is the policy that maximizes the total reward. And just to note that policy is how an agent behaves in a given situation or state. Now, Q-learning is a value-based reinforcement learning method to solve problems, and so we can dive a little bit more into these value-based methods. So, value-based methods determine a value function that in turn determines a policy that's going to maximize total rewards. A value function is a function, so it has some inputs and it generates an output, and depending on the inputs, there are two types of value functions. We have state value functions, represented by V, and then we have state action functions, represented by Q. But now, states, actions, what are those? A state is a snapshot of the environment, and an action is the decision taken by an agent in an environment. So the state value function will take a state as input and output a real number, whereas the state action value function will take the state and action as input, and it'll output a real number. So this real number is also known as a Q value. Ooh, Q. So we're getting close to Q-learning here. Now, the state value, that is VFS, will quantify how good is it to be in a given state S, whereas the state action value, or Q value, will quantify how good is it to be in a state S and then take an action A in this state. For Q-learning, we are interested in learning the state action value function. Because it's a function, you can think of it more easily as a table of rows being states and columns being possible actions, and each cell value will actually be the Q value for that given state and action. And the goal of Q-learning is to effectively learn these Q values such that the total reward is maximized. So let's see how it works with this grid world. So this here is a fully observable environment with 9 squares, and there's a plus 10 reward square, a minus 10 poison square, and other rewards is -1 for any other square. Now, the goal of our agent is to get to this plus 10 reward spot in the best possible way. And more technically, we want the agent to learn an optimal policy. This is known as the target policy. And let's say that in order to learn this optimal policy, we want to use Q-learning to do this. And so we need to make use of this Q table. Let's initialize these values to arbitrary values. Now, note that these values could also be loaded by some other agent that explored the environment previously, but for now, let's just keep them arbitrary. Now, let's say that the agent starts in the first cell at state S1, and it takes an action based on an exploration policy. This means that the actions that an agent takes is simply based on random chance, and the agent won't just choose a state because it has a high Q value, for example. And this policy is known as the behavior policy, and it can be just about anything. If the agent is in a state S1, it can take an action of either going right or going down. And because the policy is random, let's say that the agent made the decision to go right. So the action is taken, and then when taking the action, the agent transitions into another state. And let's say that this another state is S2. And on doing so, it also receives a reward of -1. Now, let's calculate the observed Q value. So this is given by the Bellman equation. Now, the Bellman equation defines a recursive relationship between Q values. And for more information, you can check out my video on the topic. But for now, the Q value for this state S1 and right is given by the sum of the reward of state S2 plus the maximum future Q value for that state S2 that we can get. And gamma here is a discount factor just to show how much we want to value the current reward over future rewards. And so if we just plug in some values, so the reward from S2 is -1, let's say that gamma, that discount factor, is 0.1. And then we multiply that by the maximum possible Q value that we can get from state S2. Now, looking at our Q table, we can see that we get the maximum Q value by going down from the state S2, which is 1.5. So substituting 1.5 in our equation, we'll get the overall Q value as -0.85. This is the observed value for Q1, state S1, and going right. But the value at the table for this specific Q value is 1. There's clearly a difference, and this difference is an error that is known as a temporal difference error. It is called the temporal difference error because we are comparing Q values of two different time steps, and their difference is the error, hence the name. For more information on this topic, I created another video right here. But for now, temporal difference error is now going to be the observed value minus the expected value, which will turn out to be -1.85. We now update the Q value in the table based on the formula that looks like a gradient update rule. And here, alpha is going to be the step size or the learning rate, so to speak, and it defines how much in every time step are we willing to change these Q values. Higher the value, faster the learning because bigger the updates. So in this case, let's also just take it to be some 0.1. And plugging in these values, we get 1, which is the expected value, plus 0.1 times the error, which is -1.85. And then doing the math, you will get 0.815 as the final result. And so we update this single Q value in the table from 1 to 0.85. And this is the end of our first time step. Let's now walk through another time step just to make sure that we understand what's going on. So let's say that now we're in a state S2 in time step 2, and we can take the action of either going right, left, or down. And the policy we are following is now random, so let's say that we choose to go down. We take the action, and then on taking the action, the agent will transition into another state. Let's say it's S6, and it receives a reward of -1. Now let's calculate the observed Q value that is given by the Bellman equation. So the Q value observed is going to be the reward in transitioning into state S6 plus the discounted maximum value that we can obtain for state x6. And so we know that the reward for state S6 is -1. And from our table, when we are in state S6, the maximum possible Q value is going to be 1.7. And this is the value if we choose to go in the downward direction from S6. So we substitute that in the equation and we get -0.83. Now, this is the observed value, but the expected value that is stored in the table for this cell is 1.5. And so, the temporal difference there is going to be the difference of the observed minus the expected. -0.83 minus 1.5, and we'll get -2.33. And now, we are going to now plug this value into our update rule for the temporal difference error. And so, this gives us a 1.5 for the current Q value expected, plus 0.1 times the temporal difference error of -2.33. Doing the math, you get 1.267, and so we update the single Q value in our table. And this is the end of our second time step. We repeat this until the sequence of steps is over, that is until we get to the +10 spot or the -10 spot. And this sequence of steps until now is known as one episode. We can then perform multiple episodes over and over again, choosing random actions and effectively just learning the values of the Q table until they become more stable. And effectively, these Q values are learned. And once they are learned, an agent can take an action based on which will give us the highest Q value result. And so the Q value will dictate the policy to get our reward. And this new policy, remember, was the target policy that we were trying to achieve. And note that this is different from the behavior policy that we use to explore the environment in order to learn effectively the target policy later on. Because we can decouple this behavior policy for collecting data from the target policy, which is used when we have an optimal Q table, Q learning is known as a type of off-policy algorithm. And so I hope Q learning makes sense, at least at this surface level. So reinforcement learning is one of the three major ways in which machines can learn. And specifically, reinforcement learning is learning what to do, that is how to map situations to actions, so as to maximize a numerical reward. Now, a function that maps a situation, which is a state, to an action is known as a policy. And it's these policies that are used to maximize a numerical reward. And so, reinforcement learning is essentially learning a policy to maximize a numerical reward. And in order to learn this policy, reinforcement learning algorithms are used, and Q learning is one such popular off-policy reinforcement learning algorithm. So what makes Q learning off-policy? Off-policy reinforcement learning algorithms make a crucial difference between two types of policies. So the first is the policy that's used to take action and actually navigate the environment. The policy followed is known as a behavior policy. And the second policy is the policy that is used to actually learn. And in the Q learning case, it's the policy that is used to update the Q values in a Q table, for example. And this is a target policy. Now, for off-policy reinforcement learning algorithms, the behavior policy can be different from the target policy, while for the on-policy algorithms, these two policies need to be the same. And this is a very critical difference between on-policy and off-policy algorithms. So that's going to end pass one. But for more details now, let's dive into Q learning specifically and also discuss why Q learning is an off-policy algorithm in more detail. So let's take a fully observable grid world of 9 squares. So you can see here that there's a +10 square, a -10 square, and everything else is -1. And the goal for agent is to start in the top left corner and to get to the +10 reward spot, making the best possible set of actions. And so we want the agent to learn an optimal policy. and we say that we want to use Q-learning to learn this optimal policy. And to use Q-learning, we need to use a Q table that will help us dictate actions. And so this Q table will have a set of rows that are states, a set of columns that are actions, and each of these are randomly initialized. Now, to begin the learning process, the agent actually has to navigate the environment using a behavior policy. And let's say that this behavior policy is that of random exploration. That means that at any given state, whatever the state that this agent is in, it will just generate some random action. So let's say that the agent is in state S1, and from here it can move either right or down. Because the behavior policy is random, let's say that the agent randomly chose to go right. So we take the action, and we receive the -1 reward, and now we are in a new state, and let's call it S2. Now, let's calculate the observed Q value. This is given by the Bellman equation. And the Bellman equation, by the way, defines a recursive relationship between Q values. And for more information, I would recommend checking out my video on this topic. So the total reward observed is the reward that we receive in transitioning into state S2, plus the maximum possible reward that we can receive when being in a state of S2. Gamma here is a discount factor that describes how much importance we want to give to future rewards as opposed to immediate rewards. It's a number between 0 and 1. Now, in order to determine this second term, we need to look at the maximum Q value from state S2. So we go to our table, and then we see that the largest value is taking S2 down, that's 1.5. And so we can use this in our equation that is -1 plus, let's say the discount factor is 0.1 times 1.5. And doing the math, you get -0.85. But the value now stored in the Q table for S1 right is 1. And the difference of this error is known as the temporal difference error. I have a full video on this topic for more details. But essentially, plugging the values in, you get -0.85 as observed, minus the expected value, which is 1. You get -1.85 as that error. And now we update this value in the Q table based on a formula that looks like a gradient update rule, where alpha here is going to be a step size or learning rate, and we'll keep it something like, again, 0.1. The first Q value is going to be 1, plus alpha 0.1 times the temporal difference error, which is -1.85. And doing the math, we get 0.815 as the new Q value. And so we update the single Q value in our table. And this is the end of our first time step. Now we can continue to do other time steps like this until the agent hits +10 or -10 and update the Q values accordingly for every time step. And this will be the end of one episode. And you keep on executing multiple episodes like this until the Q values in the table become more stable. Now, for a complete breakdown of Q learning, check out the full video. But for now, let's actually backtrack to the beginning towards that initial Bellman equation. In state S1, we took an action of right according to the behavior policy that was random. But we updated the Q value of state S1 based on the target policy, which was greedy. Now, looking at this Bellman equation, the next action chosen is simply the one that gives us the largest Q value, and this is the one that involved choosing the downward action. Note that we did not take the action going down because that down was chosen by a target policy, not the behavior policy which is used to traverse the environment. So, overall, typically for off-policy algorithms, the target policy is greedy. We're trying to find the action that maximizes the current estimation of Q values, for example. Whereas the behavior policy can be random, it could be epsilon greedy, or it could be greedy itself, or anything. But it's important to note that these two policies can be decoupled from each other. And so, for example, a behavior policy can explore the environment and collect data, and the target policy, which is used to update Q values, can be done separately from that behavior policy of navigating the environment. And because they can be effectively decoupled, This is an off-policy reinforcement learning algorithm. This is the end of Pass 2, and I hope we now understood a brief understanding of Q-learning as well as what makes Q-learning an off-policy algorithm. Now let's move on to Pass 3, where we're actually going to introduce on-policy into the mix, and we're going to actually compare their algorithms here one by one. Now, this algorithm here is the same off-policy strategy that we just discussed. So let's just walk through this really quick though. So first of all, algorithm parameters with step size, that is the gradient update here, is going to be a number between 0 and 1. Now we initialize all the Q values in the Q table, and now for the first episode, let's say that we were in state S1, and for the first step, we will choose an action A. Now, this action in the next step is going to be taken. Because it's actually going to be taken, that means that the agent uses it to navigate the environment, so that means this action should be chosen according to a behavior policy. Now, the behavior policy that we chose in our example is a random policy, so it would just choose a random action, whatever the state S is. But here, another example that we could have chosen was epsilon greedy. So we now take this action, and then when we take an action, we will observe a reward and then transition into a new state. This could have been S2, for example. And this equation over here is just the combination of all three equations that we just talked about. Just the Bellman equation from this part, and then the temporal difference error for here, and then the gradient update rule equation that we discussed too. Now, you can see here that we have like another action that needs to be chosen over here. But this action is chosen to update the Q table value. That means that this action needs to be chosen based on a target policy. And the action that is chosen has to be the maximum Q value we can get from a given state, which means that it has to be greedy. In our case, it was S2 and down. Note that this action was just chosen, but it was actually never taken. And this is kind of what allows us to decouple the target policy, which is greedy, from the behavior policy, which could have been anything, like we mentioned before. Now we transition to the next state, and then we repeat the process again and again until the end. So that was the off policy setting. Now let's try to see it from a bird's eye view of how it's different from this on policy algorithm. So the on policy algorithm we're going to talk about is known as SARSA, and it starts out very similarly, where we define a step size and an epsilon term. Now, we start with choosing an action A, depending on a policy. But note that this action A is immediately taken. So if we take the action, that means that this action A has to be chosen based on a behavior policy, whatever this behavior policy may be. Now, when taking the action A, we would have transitioned into another state S- and received a reward R. Now we're in this new state. Now we can choose another action, A- from this state, but based on another policy. And this policy, you can see, is being used right over here, and it's being used to update the Q value itself. That means that this action that we're taking needs to come from a target policy. Now, what's really important is this next line, where we assign A- to A, and then we take the action A. That means effectively, whatever we chose here in the previous form of that loop, we're actually going to eventually take that same action. So even though A- was chosen as a part of the target policy to update the Q values, we're taking the action, which means that it should also be a part of the behavior policy. And this is why the behavior policy and the target policy must match each other, because the policy that we're using to explore the environment actually is the same policy that we're using to learn these Q values. And hence SARSA, which is the algorithm that we just discussed, is an on-policy algorithm. First, a policy is a function that maps a state to an action. Q-learning is a reinforcement learning algorithm that learns a policy that maximizes total reward. And the policies that are the main characters here are twofold. The first is the behavior policy, which is a policy that is used to take the actions in the environment. And then we have a target policy, which is the policy used for optimal decision making. In this case, it's used to update Q values. Off-policy reinforcement learning algorithms can have a different behavior policy and a target policy, and thus they can be used to decouple data collection and training. On-policy algorithms like SARSA use the same policy for the behavior policy as well as the target policy. And so the agent takes actions and learns using the same policy. What is Monte Carlo? The name Monte Carlo comes from the famous Monte Carlo casino in Monaco, known for its association with gambling and games of chance. Monte Carlo methods use simulations to solve problems that may be difficult or impossible to solve analytically. Where do we use this? So how do we calculate the value of pi? There may be some analytical solutions to do this, but the Monte Carlo way to do this is, let's say that we have a square tray of side 1, and then we have a circle tray of radius 1. And the idea now is to randomly drop a ball onto this rectangle platform so that it can fall either in this tray, or just nowhere else. And we can simulate this random dropping over time. As the number of balls dropped increases, we can divide the number of balls in this circular tray with the number of balls in the square tray in order to get pi. And this works in theory because you can just divide the areas to get pi. Now here's a completely different application. Let's say that you want to host a game of bingo. All right, number 53?
Yes!
Someone's excited. And number 45?
Yeehaw!
Maybe a little too excited. So you know you're gonna have 500 players and you need to call out, say, 20 numbers. How many people are going to be winners at the end of this? Well, the Monte Carlo solution, like I said before, is about executing a number of simulations to simulate all of these bingo games and then try to determine that final number of people who will win. And executing the simulation, you get this wonderful graph over here. Over time, as we execute more and more simulations of all of these bingo games, you'll see that around 1% of all the players will win the game at the end. So this comes out to about 5 to 6 winners for the game. And if you want more intuition on how exactly this code is constructed and how you can code out this Monte Carlo simulation, do check out another video right here. So let's now talk about the pros and cons of Monte Carlo methods. The main pro is that they are very versatile. These similar Monte Carlo methods can be applied to very different types of problems. But the main con here is that simulations can be pretty expensive and may not be able to be applied in every single situation, practically speaking. Now on to Pass 2, where we talk about Monte Carlo methods specifically for reinforcement learning. Monte Carlo methods are used in reinforcement learning for two purposes. One is to evaluate a policy, and the other is to improve a given policy. So let's talk about each in detail with our fun, trusty robot, Frank. The policy can be thought of the decision-making brain of any agent. Based on a situation, that policy will dictate what action the agent should take. So this is Frank. Frank, say hi. Hi. What a cutie. Frank is now going to take actions based on its policy. Now it's good that Frank can make these decisions, but how is Frank making these decisions and how good are these decisions? An intuitive way to look at this is to put Frank in this wonderful grid-like world where we have rewards which are written in the squares. Well, wherever Frank starts, the goal for Frank is to get to this +10 spot without incurring a lot of the negative ones along the way. Now, with Frank's help, we are going to intuitively describe this Monte Carlo method. So Frank, you can now do your thing. 3, 2, 1. Nice. So Frank got to the goal, but how good were these actions actually? Well, for every state action pair, we can calculate the future reward in the Q table. Now, this Q table here is just an insight into how Frank's brain is working, and is an insight to how Frank thus makes decisions. For example, in the first from the last state, Frank was in a state S6 and decided to go down, and the future reward became 10. And so, Q of S6 and down is equal to 10. And from the second to last state, just before this, let's say that Frank was in a state S3, and this was when Frank also chose to go down. And in this case, the total future reward was -1 plus 10, which is 9. And so Q of S3 down is 9. And so effectively, we can just backtrack until the start to determine what the future Q values were for this episode. Now, this is great, but these Q values that we have now are just estimations based on this one episode. So why not just let Frank do this thing again? Ready, Frank? 3, 2, 1.
No, Frank! You ended up in the poison spot.
Looks like Frank was not as good as we thought and can still make mistakes. But like we said before, for every state action pair taken, we can calculate the future reward. Now, in the first from last state, we were in a state S2, and we decided to go down. So the total future reward is -10, just before we hit the poison. So Q of S2 right becomes -10. Now, in the second from last state, that is the one just before this, we were in a state S3 and we decided to go down. So the future total reward was the -1 plus the -10, which is -11. But we know that from the previous episode, we saw that Q of S3 down, that we got a +9. And so we could probably just take some average of these two. And then we just keep backtracking until the start. And we can keep repeating these simulations over and over again and estimate the Q values by taking their averages over time. And as we perform more simulations, you'll notice that the Q values over time are going to converge to a specific value, and this is due to the law of large numbers. Now, once we have these Q values, you can understand Frank's methodology and how it decides to take actions. So you can see that when Frank is in a state S1, what action will it take? Well, the highest value here is 1.5, which corresponds to down. And so chances are that if Frank is in a state S1, the greedy action that Frank will take is to go down. And so, now that we know Frank's Q table, we know how Frank behaves, and thus we know Frank's current policy. Now that we know how to determine and evaluate Frank's policy, we want to also see if we can, help Frank a little bit out in improving his policy. So now we have Frank again in our grid world. Hey, Frank.
Hi.
And now we know this Q table dictates how Frank will behave. And so for the first episode, let Frank do its thing. 3, 2, 1.
No! Poisoned again!
Alright, Frank was poisoned, but now let's actually help Frank's decision making out by tweaking the Q table. So, in the first from last state that Frank just did, it was in some state S1. And so the total future reward is just the -10 on going down. So Q of S1 going down is -10. But Frank, we want you to learn from your mistakes, buddy. So let's not be too harsh on this downward direction, and we'll update the Q value such that it takes into account your previous knowledge, but also this new information. We could assume like the weight is 0.1, and so we can calculate its new Q value. Then now we continuously backtrack to update the other Q values in this episode. Now based on this new Q table, Frank can traverse the terrain again, and then we update the Q values again. So it's a continuous dichotomy of first policy evaluation like we did before, but also there is a phase of improvement too. And we do evaluation, improvement every single time step. And each time we update, the Q table will nudge Frank into making better and better decisions over time. And so overall, we evaluated Frank's policy and improved Frank's policy with Monte Carlo methods. Monte Carlo methods involve using simulations to solve problems that may be difficult to solve or impossible to solve analytically. They are versatile but can be computationally expensive. And in reinforcement learning, Monte Carlo methods are used for policy evaluation. That is, how does Frank decide what actions to take? And it's also used in policy improvement. Can we improve what Frank's actions are? What is Q-learning in simple terms? Well, to help me explain this, we have our trusty robot Frank. Frank, say hi.
Hello.
What a cutie. Frank here is going to navigate this environment. And in order to navigate this environment, it uses a Q table. You can think of this Q table as Frank's conscience that tells Frank what to do in every situation. Alright, I see where you are, Frank. So what do you want to do here?
My Q table is telling me to go right.
Gotcha. Alright, now that you're there, what about now?
My Q table is telling me to go down.
You go for it, buddy. Now, this is a simple world of just 9 grid squares where there's a finite number of states. But what if there were a lot of states? Well, that would mean that this Q table becomes really big. Too big to fit in Frank's tiny little head. It would literally run out of memory. So instead of having this table as a conscience, it's probably better to just have a function as Frank's conscience. And this function would just take in a state and an action, and it would output some value that emphasizes how good that action was taken for the state. This value is known as a Q value, by the way. So we replace this giant Q table with a function. In the context of AI, this function is typically a neural network. So Q-learning is to learn values in a Q table. Deep Q-learning is used to learn the parameters of a Q network or a neural network. Now this Q network is randomly initialized and represents Frank's conscience. We have a target network that represents the ideal conscience, and this is the same architecture as the Q network. The goal now is to compare Frank's current conscience with Frank's ideal conscience. And from this comparison, we can compare them, get a loss, and use this loss to update the parameters in the Q network with backpropagation. And then the cycle repeats. In the next pass, we're going to get into more details, but for now, in order to train this network, we actually first need to take a step back and collect this data. So let's just talk about that very briefly. So this data collection, first of all, is done using this Q network. It's first randomly initialized, and some state is chosen. The Q network will generate the action to take. This action is taken, and then a reward is gained, and the agent goes to the next state. So the quadruple of the state, the action, the reward, and the next state is then taken and stored in some memory called the experience replay buffer. And we repeat this process of just choosing some state, producing these quadruples, and storing them. So this data is now in our experience replay and then can be later used to train our Q network, which we just discussed before. Now, there are 2 phases that we discussed in Pass 2. That is the data collection phase and the training phase. So let's talk about both in detail, starting with the data collection phase. So first, we randomly initialize the Q network. We choose an initial state, pass it through the Q network, and the number of neurons, by the way, in the output layer of this network is the number of possible actions. So each neuron outputs a Q value for the input state at a specific action. So for example, if we could only go left, right, up, or down, there would be 4 neurons in the output layer, and each of these neurons would correspond to a Q value for each of those actions. So we then choose an action in an epsilon greedy fashion. We take the action in the environment or in some simulated environment. And once the action is taken, Frank will get a reward, and Frank will also be in a new state. So now we take that quadruple that we just described, that is the state, the action, the reward, and new state, and store it into the experience replay buffer. Now we can randomly choose a new state and repeat the process of collecting the data in the experience replay buffer. And this is the data collection piece. Now, on to training. Now we have this experience replay which has a lot of data, and we can use this data to train the Q network. So let's take a batch of this data. Now, in this case, just for explanatory purposes, let's say the batch size is just one example so that we can see what's going on throughout. We feed the current state of the quadruple into the Q network. We get the Q value corresponding to the action in the quadruple. And then we also take the same current state, pass it through the target network, and we get the highest Q value there. Now we take the reward from the quadruple and add it to this target Q value. So now we have two main values, one from the target, it's an ideal Q value, and then we have the current Q value. Now we're going to compute the mean squared loss using the Q network's Q value that represents Frank's conscience, and the target final Q value that represents the optimal decision. This loss is then backpropagated into the Q network and the parameters are updated. So Frank learns, but the target network remains the same. Now we repeat the process for a few batches where Frank's conscience continues to learn, but the target network still remains the same. And then after a few batches, we will update the parameters of the target network to then match the Q network and then continue. And eventually, Frank's conscience and decision-making improves, and he's a champ. A Q table represents an agent's conscience. The deep Q networks combine Q learning with neural networks. DQN construction has two phases, a data collection phase and a training phase. The data collection collects independent quadruples of experiences in data stores called the experience replay buffer. And the training phase trains the Q network using data in this experience replay buffer. The PPO algorithm makes use of two main architectures, a policy network and a value function network. They are both neural networks that take an input and return an output. The policy network will take a state as input and it will produce an action as output. From an architecture standpoint, the output layer of this network has a number of neurons equal to the number of possible actions it can take. And each neuron is a probability that an action is taken when the agent is in the input state. The value function takes a state and an action as input, and it will output a real number that quantifies how good was this decision. This number is known as a Q value. From an architecture standpoint, as was with the policy network, the output layer of this network has the number of neurons equal to the number of possible actions it can take. And so, technically, this value function neural network will take in a state as input, and for every action, it is going to determine a Q value. And this will quantify how good was this specific output action for this specific state. To help us out, let's bring out Frank, our lovely friend. Say hi, Frank.
Hello.
What a cutie. Now, Frank is in this grid world, and he needs to know how to get to that plus 10 reward spot. Now, to do so, he can take the actions of left, right, up, or down. And in this pass, we're going to give an overview of how Frank can learn to navigate this world using PPO. So let's talk about the overview of the training process. Frank starts at some random state. The state is passed into a policy network. The policy network will determine the probability of generating each action. This is then a probability distribution, and we sample from this to determine the actual next action. Frank then takes that next action and will receive some reward. We then stored the quadruple of the state, action, reward, and action probability into a data store. This information will be useful when training the policy network and the value function network, and we'll talk about this later. We now repeat the sequence of steps for the episode, or some fixed number of time steps within the episode. Now we have data stored in this episode as a batch. And we can collect multiple batches if we choose. But let's just stop over here. Thanks for the help, Frank. We'll take it from here and we're going to help you learn. Okay. Nice. Now let's talk about training the two networks. Take the batch of the state, action, reward, and action probability. Now the state and action are used with the value function network to give us a Q value. And like we said before, this will quantify how good do we expect this action to be. We then determine the total future reward for every time step using the data that we stored. And this will quantify how good did we actually perform. We take the difference between these two values, and this difference is known as the advantage. We use this advantage in order to compute a loss. This loss is then backpropagated through the value function network, and so it learns. We then use the same advantage and probabilities that we stored previously to determine the loss for the policy network. The loss is backpropagated through the policy network, so its parameters are updated. And then we repeat this process for all batches of data. Effectively, the policy network and the value function network get better over time as they learn over time together. And Frank learns to make better and better decisions so that he can get to that plus 10 reward square. And this is an overview of the one iteration for proximal policy optimization. So in Pass 2, we saw that the value function network and the policy network are trained together. And the overview of the steps is basically we compute the loss for the value function network, we compute the loss for the policy network, we update both networks together, and repeat, and then Frank becomes better and better as a decision maker. Let's now take the overview of the process that we discussed in Pass 2, but we're going to add a few more details specifically along the loss function calculation. So let's start with the value function network and generating its loss. So we get the batch of data for the episode that we stored in Pass 2. For each time step, we compute the actual future reward with the data gathered. And this is done by taking the sum of discounted future rewards. And then we can compute the expected future reward by passing the state into the value function neural network, and it produces a Q value for every action. And then we look at the Q value for the specific action neuron in our tuple. So for every time step, we have two numbers. We take the difference between these two numbers to get the advantage. We square the advantage for every time step, and we can take the average of this across the batch. This final number is a loss that we backpropagate through the value function network, and so the neural network learns. And at the same time all of this happens, we are also training the policy network. So let's see how that's going. Now, if we write it in mathematical form, the policy network loss looks like this. Very cumbersome, but let's explain what's going on. First, we'll get the batch of data that we stored. Next, pass the batch of states to the policy network to get the probabilities of actions. In each case, we only consider the probability of the action taken when we gathered the data. We then divide two numbers, that is a probability for the specific action that we have now, divided by the probability we collected previously. And this is a probability ratio. We'll multiply this ratio with the advantage computed in this time step. And so for every time step in the episode, we have a number. Let's keep this number aside and hold on to this, Frank, for me, okay?
Okay.
Nice. Next, we take the probability ratio and we'll clip it to ensure that we're not changing the network too much. We multiply this by the advantage, and so now for every time step we have two values. We'll take the minimum of these values And then when we take the average of the values across the batch, we'll get a single number. This single number is our loss that is backpropagated through the policy network. So this is quite a bit of steps, but overall, the loss function strikes a balance between making effective policy updates to improve performance and making cautious policy updates to improve stability. And effectively, the value function network and the policy network are trained together, and that is PPO. Proximal policy optimization algorithm is used to learn a policy directly. Now, the PPO algorithm makes use of two architectures, a policy network and a value function network. The policy network predicts a probability distribution of actions, whereas the value function network predicts Q values for every action taken from a state. The PPO algorithm involves training a policy network and the value function network iteratively and together. And just as a new tidbit here, but this algorithm is actually used by ChatGPT and other large language models today to ensure that the responses that they give are safe, factual, and non-toxic. For this first pass, let's have Frank help us explain. Frank, say hi.
Hello.
What a cutie. Now, this here is a grid world where there's 9 squares and each square has a reward inside of it. The goal for Frank is to get to this plus 10 reward spot. And to do so, Frank makes decisions, that is to go either left, right, up, or down. But Frank doesn't know how to make any decisions to begin with. And so, Frank learns. Maybe by interacting with the environment, and he does so by using a reinforcement learning algorithm. We've discussed details about a few of them in previous videos, so you can check them out for specifics. But effectively, once Frank learns how to make decisions with any of these algorithms, he will effectively be able to get to that plus 10 reward spot efficiently. But wait, can we help Frank out even more? And it turns out that we can. So while Frank is learning with a reinforcement learning algorithm, us humans can also provide our feedback to Frank as a mentor. This allows Frank to learn faster, and it also allows Frank to give responses that are more human-favored. Alright, Frank, get over here.
Yay.
In this pass, we're going to show you how Frank learns without human feedback and then add in human feedback and see how that affects things. So, want to get us started, Frank?
Sure. Let me go down. Let me go down. Let me go right. Oh, bad spot. Learning now. Starting over. Let me go down. Let me go right. Let me go up. Let me go right. Let me go down. Let me go down. Good spot. Learning now.
Great, so Frank will keep doing this as he learns, but now let's see how a human can help.
Starting over. Let me go right.
Alright, Frank, so that's fine.
Let me go down.
Okay.
Let me go left.
I would prefer you actually go right here.
Okay, going right. Let me go down. Good spot. Learning now.
So in this situation, Frank was following an algorithm, but I was still nudging him in the direction that I thought was the correct direction. In this pass, let's talk about how ChatGPT makes use of reinforcement learning through human feedback for a practical application. It's split into 2 parts. So first is train a reward model to be a human advisor to ChatGPT. And then the second is use this rewards model along with an algorithm called Proximal Policy Optimization to fine-tune ChatGPT. Let's talk about each part now, and starting with the rewards model. This model is a GPT architecture that takes in a question and answer as input, and the output of this GPT network is a number. It's a score that says, how good was this answer to this input question? Now, higher the score, better the response. And our goal is to first train this model. We can do this by putting a question to a pre-trained chat GPT multiple times, and each time we'll get a unique answer. We as humans then take these responses and we rank them based on which was the best response versus the worst response. And we use this then to train the rewards model. And once the rewards model is trained, it should be able to assess how good a given answer is to a given question. So that was the first part, which dealt with training the rewards model. Now on to the second part, where we use this rewards model along with proximal policy optimization in order to fine-tune ChatGPT. So ChatGPT is given a question, it generates a response. Now this response is generated using the reinforcement learning algorithm called Proximal Policy Optimization. Now for more information on how PPO works, I recommend you check this video out. It's a good one, you won't regret it. This response along with the question is passed to the rewards model to generate a number. That's a score that tells us how good was this response to this question. Now we use this reward in the loss function for ChatGPT's network. We now perform backpropagation so that ChatGPT learns. Now this is just one iteration, but we keep doing this for multiple iterations, and once trained, ChatGPT becomes this public-facing app that it is today. For a more deep dive on the entire process for ChatGPT, you can check out my playlist of videos right here. But overall, I hope you understand the real-world use case of reinforcement learning through human feedback. Reinforcement learning through human feedback is a framework that integrates human feedback into the training process of a reinforcement learning algorithm. Now, the reinforcement learning algorithm in question could be DQ learning, proximal policy optimization, or any other algorithm. Human feedback is used to guide and accelerate the learning process, allowing the algorithm to make more informed decisions. And in ChatGPT, human feedback is given via the rewards model. The iterative training process with reinforcement learning through human feedback enhances ChatGPT's capabilities, making it a powerful tool for generating high-quality responses. And that's going to do it for today. So I hope this video helped you get a good sense of what is reinforcement learning through human feedback and where it is also practically used in the guise of ChatGPT. And that's all that we have for today. I hope that this compilation of videos helped you get a foothold of what reinforcement learning is, certain learning procedures along the way, and even some code. So thank you all so much for watching. If you do think I deserve it, please do consider giving this video a like and subscribe for more amazing content, and I will see you in the next one. Bye-bye.